The next thing I'd like to look at, guys, is, and this is the last little bit of this chapter, it's got to do with reaction profile diagrams. So essentially in a reactant profile diagram, what it does is describes how reactants and products are related in energy. So just like any graph, on the y-axis, as you go up the y-axis, it increases, and as you go from left to right on the x-axis, the values increase. So the progress of the reaction, in other words, you could say time here, as time goes on as the reactants occur. Now, when reactants collide, this energy that I talked about in another video, this activation energy, the energy necessary to crack the shell, if you like, that's described here as this amount. It doesn't actually, it's not included in the initial or the final levels of energy. You know, if you draw a straight line across from here and draw a straight line across from here, because obviously that was gained during the reaction. The reactants didn't have that at the start, and that's why you have this peak here. But if you were to talk about the energy lost and gained in this reaction, you will be talking about the difference between the two of these. Now that's described as delta H, but it's just between here and here, because of the fact that this energy is just to get over the hump. It's a bit like rolling a boulder over a hill. You must roll the boulder along, and then if you want to get down to this point, you can't but go over here. Even though it means you go higher than you were, the actual change in distance will, from start to finish, will be between here and here. And that's why that little hump is there in the diagram. That is known as activation energy. Sometimes you can think of this as, you know, striking a match. Striking a match produces sufficient energy so that maybe your reactants, leaves or little bits of wood or whatever you're burning, go to carbon dioxide, water and unburnt hydrocarbons, whatever is left over. So this, if you like, the striking in a match would get you from point here to point here. A low activation energy, you know, if there's a small peak, there's always some activation energy because, you know, reactants, but room temperature, as you know, a lot of reactions occur at room temperature. Room temperature is a lot of the time enough energy for a reaction to occur. And then we put things into the freezer and that to try and reduce the levels of reaction. Put things into the oven and we allow things to get over the hump of the reaction. Cooking is actually a chemical reaction. It's called caramelization, and it's where you convert the, if you like, the stuff, the dough beforehand. It is actually converted into new products in the process of cooking. Sometimes people aren't sure it's cooking a chemical process, but it is. The reaction process, here you see the peak is much higher. And that means that effectively you would have to supply more energy to go from the reactants to the products. But again, funnily enough, like that energy is not gained by the products here, obviously, or the reactants. The difference in the two, or delta H, is just between here and here. Now we will look at this again in fuels, because it's quite important in fuels to get the most out of it. But to show, the reason we're looking at this point is, effectively, as you see from this diagram, a catalyst, it doesn't actually lower the activation energy of that route, if you like. It gives a different route. So to go back to the analogy earlier, instead of rolling the boulder over the hill, we drill a hole through the hill. Now you know how difficult the reason the catalysts are so good or are so effective is they are very good at providing an alternative route. And that's essentially what they do. So sometimes what will come up in an exam question, you should know I need to represent this diagram, but for yourself, so you have it clear, because it's a nice way of representing how the catalysts work. But just remember that, number one, that it provides an alternative route, and as you know, catalysts alter the rate of a reaction, but they also alter the route of the reaction, giving rise to a lower activation energy. Therefore, more of the reaction will occur at that temperature. So you don't change the temperature, you give an alternative route. So that's why you're a little bit careful with the words there. And you will be expected to draw something similar to that as well. Again, to run through, if you were to talk about each of the things that we did at the start of this chapter, and one of the videos I gave you earlier, like the nature of the reactants, the particle size, the concentration of the catalyst, all of those things can be explained through the use of the collation theory. Because these factors are affected effectively by, like if we were to talk about the nature of reactants, bonds will break in covalent compounds, requires more energy. Therefore, the molecules must collide with a greater force. Particle size, if there's more surface exposed, then there can be more collisions. Again, the collision theory. The concentration, if there's more of the molecules there to collide with each other, then more collisions will take place. And finally, the catalyst, it will alter the path of the reaction, if you like, and that path will have a lower reaction or a lower energy, a lower activation energy. The interesting thing here is actually you can get catalysts that actually slow down the reactions as well. You can actually get a catalyst, a glycine that you can add to hydrogen peroxide, let's say, to do the opposite of manganese dioxide or do the opposite of potassium iodide. Both of those speed up the decomposition of hydrogen peroxide. But it's interesting that in the case of glycerine, what it does is it slows down the decomposition. So in a lab, if you want to hold on to the hydrogen peroxide you have, you'd add some glycerine to it. That effectively, guys, brings us to the end of rates of reactions.